In this video, we will discuss the concept of reaction enthalpies. Now, the enthalpy of a reaction is just the quantitative value of the amount of heat involved in the chemical reaction. The symbol for enthalpy of reaction is delta H, and sometimes chemists like to append subscripts to these variables in order to be a little bit more specific as to what type of reaction we're talking about. So for instance, here we have our generic reaction, delta H Rxn, but we can also use enthalpy of neutralization, enthalpy of combustion, or even enthalpy of a phase change, such as vaporization. This may seem a little strange because this is not a chemical reaction, but it is change that involves heat and energy. In this last example, we have an interesting one. We have enthalpy of formation. Notice that we're making carbon dioxide from its constituent elements. This becomes important later on when discussing Hess's law. Now, regardless of the subscript, the information provided is always the same. Now, the symbol for enthalpy of reaction is delta H. Now, where does that come from? Well, we can't actually measure the inherent enthalpy of a chemical, but we can measure the difference in enthalpy between, say, a reactant and its products. So, if we have reactants of some reaction, and we have our reaction progress, and as the reactants slowly become products, the products are going to have a different enthalpy than the reactants. Now, this difference in their enthalpies, as we remember under certain conditions, is the same as Q, or heat. And when it comes to change, or delta H, as we learned in physics, delta is just the final state minus the initial state. Well, here, final state is the enthalpy of the products, initial state is the enthalpy of reactants. In this case, because products have a higher enthalpy, our enthalpy of reaction is going to be positive, which means this is an endothermic reaction. We had to put energy into the reactants to get them up to products. Now compare this to the opposite scenario, where the enthalpy of the reactants is higher than that of the products. In this case, we still have the same delta H, but the reactants lost energy to become the products. And because the enthalpy of the products is less than that of the reactants, in this case, the delta H, or the enthalpy of reaction, is going to be negative, making this an exothermic reaction. And so another way of looking at this is that when a reaction is endothermic, it has a positive enthalpy, then we can treat heat as a reactant, as opposed to an exothermic reaction, where the enthalpy of reaction is negative. We can treat heat as a product. Now, if we look at this information from a stoichiometric point of view, we notice that in this example, the enthalpy of neutralization of 1 mole of hydrochloric acid is going to give us 58 kilojoules of energy out. Well, what else does this mean? Well, it also means that if we neutralize 1 mole of sodium hydroxide, we are also going to get 58 kilojoules of energy released. And if, say, we want to neutralize 2 moles of hydrochloric acid, if we use the enthalpy of neutralization as a conversion factor between moles of hydrochloric acid and energy released, we're going to get twice that. We're going to get negative 116 kilojoules, or 116 kilojoules released. Now, in some older textbooks, we often see enthalpies of reaction listed in kilojoules per mole. Now, this isn't too confusing in this case because all the stoichiometric coefficients in this reaction are 1. But what if we had a reaction like this, the combustion of methanol? When they say the combustion of methanol releases 1077.4 kilojoules per mole, what do they mean? Well, it's a little confusing, which is why we don't always like to use this per mole unit when it comes to enthalpies, but sometimes we do see it, and we do need to understand what they mean. So let's do a stoichiometric reaction involving energy. Let's take 55 grams of methanol and determine how many kilojoules of energy are released upon its complete combustion. Well, according to the stoichiometry of the reaction and the enthalpy of this combustion, we're going to get out 1077.4 kilojoules per 2 moles of methanol, or per 3 moles of oxygen consumed, or 2 moles of carbon dioxide and 4 moles of water produced. That is what the stoichiometry and the enthalpy of neutralization is telling us. So we have to pick the correct one when we're converting 55 grams of methanol and completely combusting it. Now, because enthalpies of reactions are always per mole, we have to convert our 55 grams of methanol into moles. So we use the molecular mass, and now we choose the appropriate stoichiometric ratio in order to convert moles of methanol to kilojoules of energy. And if we do everything correctly, all of our units should work out, canceling out to give us just kilojoules. So 55 grams of methanol completely combusted will release 1,900 kilojoules of energy. Now, it is important to note that reaction enthalpies are very flexible in their use. For example, here we have our decomposition of HCl into hydrogen and chlorine. This requires, or it's an endothermic reaction, absorbing 184.6 kilojoules of energy. But what if we wanted to go in the reverse? What if we wanted to create hydrogen chloride from hydrogen and chlorine gas? Well, it turns out the amount of energy involved is the same, except the sign is the opposite. So instead of absorbing 184.6 kilojoules, we are actually releasing 184.6 kilojoules of energy upon the reverse reaction. This may seem a little strange, because we can't always reverse every single reaction. There's a little bit more involved with that. But it doesn't matter if you need, say, enzymes, or if you had to put a little spark in your reaction. The change in energy between the reactants and the products is the same, but just going in a different direction. And if we wanted to double the amount of hydrogen chloride that we decompose, well, we're just going to double the amount of energy absorbed. And if we want to cut it in half, well, we're just going to divide the amount of energy absorbed in half. Now, you may say that we're not allowed to do this because we have unbalanced reactions. Well, they actually are balanced, but their stoichiometric ratios aren't in the lowest whole number ratios. Well, we can do this in thermochemistry and thermodynamics as long as we understand what we're doing. And it becomes important to be able to do this and understand its effect on the enthalpy of reaction later on when discussing Hess's law.